Good morning everybody. I have been talking about this topic, identification of genesis of quality problems in steel products through metallographic investigation. For the last 1 or 2 lectures I have talked about this. So, what basically I have talked is how you do the investigation, metallurgical investigation, how to inspect the product, to identify the location, size, shape, frequency and occurrence of defect, and you preserve and observe the defect, and then careful cutting of samples for metallography, then transverse section which has to be polished, sometimes etched. These are the different common requirements. Then you actually observe it. What do you observe? Whether there is scale associated change in the microstructure due to the defect, whether the grain coarsening has been there, internal oxidation has been there. These all gives, these symptoms are very important. This gives very important clues so as to what has created the defect, where from it has generated. Then the location of the exogenous NMI, whether it is large or what is the size. Then elemental information using, I had mentioned earlier that whether using energy dispersive or wavelength dispersive analysis to identify of X-rays, to identify the chemistry and source of NMI. These are all important. Then to correlate the defect incidence with steel grade or process variation, consolidation of all possible clues. Finally, we have to do using expertise or process knowledge. And then these are I had mentioned that what are the manifestations, quality issues. It can be surface lamination, it can be thin line, it can be cracks or holes or subsurface or internal locations defects. Genesis, mainly I have been talking about inherited from the input material, that means whether it is exogenous entrapment during steel making or casting or subsurface imperfection in casting. This may be grade specific, may be process related. So, the identification is very important. Because why it is important? Because then only we can implement the remedial or improvement measures, so that these defects do not recur or they can be controlled within limits. I had mentioned about certain common defects, which is edge crack in austenitic stainless steel, but chemistry balance between austenite and ferrite is very important. HR thickness is very important. Thinner the hot rolled coil, hot rolling product, more is the possibility of edge crack formation. So, we have to be careful. Then I have talked about surface lamination, how it is forming, how does it look like. Then sliver line, very thin slag line, where from it is coming mainly. I have talked about tearing or hole, talked about transverse crack. So, these are basically material defects I have mentioned. So, they are originating from the cast material, parent cast material, not during processing subsequent. There can be defects existing at surface of cast slab or bloom or billet. They may be related to the chemistry of the grade or influenced by the process parameters, or there might be entrapment of large exogenous NMI during steel refining or casting. Reoxidation may be a problem, nozzle clogged product. What are the sources of NMIs? Reoxidation, nozzle clogged product, slack from ladle, tundish, mold, maybe refractory erosion. These all I have mentioned. Then I have mentioned the critical size of inclusion, the large inclusion. Some people tell 100 micron, some people tell 50 micron. These are what we have to be really bothered about. There may be very fine large number of inclusions. You see 1 kg of clean steel contains large number of inclusions, maybe 10 to the power 7 to 10 to the power 9 inclusions. Just imagine how many, but only few of them are really large, maybe around 400 of 80 to 130 micron, 10 around 130 to 200 micron, only one is 200 to 270 micron. All others are very, very small and they are really benign, harmless. So, average volume content or size is not important. What is important is number and distribution of large inclusions. If you see total number of inclusions are quite high, So, the total number is of no use. What we will be really looking at is the large inclusions more than 50 or 100 micron. Those we have to be very cautious about, because those are the real defect issues, they will be creating problem. So, today I will be giving you certain examples of quality problems. While doing metallurgical investigation, the whole topic have been for the last 2 sessions metallurgical investigation, how you do metallurgical investigation, so that to unravel the source of the quality problem. That is the whole idea, to know where from these defects are originating, the genesis, at what stage of steel making or casting they are getting generated. That is the purpose. Now, I will give you some examples of quality problems during metallurgical investigation as they are getting manifested or getting revealed. I will give you certain examples. I have told you that poor macro cleanliness caused by large, maybe more than 100 micron exogenous slag entrapment is a real problem, which causes surface defect or subsurface defects or maybe internal defects in steel, for which the quality can be impaired. The steel might get rejected during testing or in the process of application when it is being used, it might get into problem. There might be a crack formation, there might be a failure of the particular steel grade. So, I am giving you here 2 examples of large inclusions. This one, this is a surface defect which has come on a roll product. So, it has been analyzed through electron probe microanalyzer, that means the EDS attachment and WDS attachment of the SEM to identify what is the nature of this entrapment, which has caused this problem, which has caused this defect, surface defect, and which is visible. The defect has been visible on the surface and the material got rejected. So, it has been found that it is calcium aluminum silicon oxide, that means a complex silicate of calcium and aluminum, which is causing this failure in magnetic particle test. This failure has occurred during magnetic particle test. That means, sometimes even if the defect is not visible, you have to do magnetic particle test to identify whether there has been any subsurface defect. So, this has been revealed through magnetic particle test, this defect, and it has been traced to entrainment of slag of calcium aluminum silicon. That means, it might have got entrapped during in the secondary refining stage. So, this is one typical example of how defects look like, and then through investigation we trace back to at what stage of steel making or refining or casting it has got entrained or entrapped. Next, this one, this another one defect, just if we look at this, we have this has been revealed during blue fracture test. It is basically blue fracture test is a typical test for evaluation of macro cleanliness. Micro cleanliness, what we see under optical microscope at say 100 magnification, we identify what are the inclusions, what are their size, shapes, and then we can know whether these are A, B, C, D, 4 types of inclusions are there, sulfides or oxides, globular oxides or different types of silicates or something like that. But there are certain tests for macro cleanliness, because as I have mentioned, what is most important in steel is, or what is most problematic in for steel quality is the large inclusions, which you may not see under normal microscope, because under optical microscope you see inclusions which are micro inclusions, which you have to see under microscope. But really what is problematic is large inclusions which are say more than 50 or 100 micron in size. Now, such macro cleanliness can be evaluated through a blue fracture test. What is it? You heat the steel sample, is a standard test, STM test, at say 250 or 300 degrees centigrade, and then at that particular temperature, if you break the sample with a notch and all, on the fracture surface, the sample becomes blue because it has been heated to 250, 300 degrees centigrade, it is blue. So, in the blue sample on the fracture surface, you will see inclusions which are relatively white or grey in color. So, this can be easily distinguished or delineated. So, in this standard blue fracture test, certain inclusions have been revealed. So, now what are these inclusions, where from they have come, we have to know that, then only we can take care of these inclusions while we make steel subsequently. So, it has been revealed that these inclusions, these tricksome inclusions, long inclusions in the rolling direction, these are basically complex oxides of calcium, aluminum, silicon, magnesium. That means, basically these are silicates of calcium, aluminum, magnesium. These are complex oxides. This has come from again from slag. So, this has caused this entrapment of slag has caused this macro cleanliness problem, which has got revealed during blue fracture test, and the this particular product got rejected at this test level. So, these are typical examples of large inclusions, one during magnetic particle test it got revealed, another during blue fracture test it got revealed, and using these large inclusions we have tested these inclusions under SEM with attachment of WDX or EDX to know what are the elements present, and from there to know what are the actual constituents. So, we have found out these are basically entrapments from slag. So, what I am telling you or giving examples is how metallurgical investigation can reveal the sources or the origin or the genesis of exogenous large entrapments which are causing these defects, problems, quality problems. Now, earlier I had mentioned that high delta ferrite, which is more than 6% delta ferrite content in austenitic stainless steel, say ASI 304, standard stainless steel, austenitic stainless steel, it creates H crack in HR coil. Now, we have through metallurgical investigation we have found that the ferrite content, when it increases, say if it is up to say 7% in this case, you do not find here there is no H crack. So, if it is up to 7%, there is no H crack ferrite content, but as you are increasing the ferrite content, there is a possibility of increase in H crack. So, what we have to do, suppose you have 8% ferrite content. So, there is a possibility of H crack formation if the finishing temperature is low. So, we have to increase the finishing temperature to say 960 degrees centigrade, then only you can take care of this H crack, you will not find H crack. But if you finish at lower temperature, say at 940 or so, there is a possibility of getting H crack. Similarly, if you, as you are going to higher and higher ferrite content, the things become more difficult. You have to be more careful during hot rolling. Hot rolling temperature has to be more. So, you look at here, say about 9.5% or so. So, even at 960, a lot of H cracks are forming. You have to go to maybe 980 degrees centigrade finishing temperature, that means higher finishing temperature, to get coils which are free from H crack. So, what is important is to understand that ferrite content is created by chemistry imbalance. That means your chemistry has to be such that ferrite content is not more, it has to be less than, preferably less than 6 or 7%. But if it is slightly more, then you can salvage the situation by finishing the hot rolling at higher temperature. So, this is what is the way out. We know from the chemistry, because the chemistry will dictate what is the ferrite content, and if we know that ferrite content is slightly higher, say more than 8%, then what we should do? We have to finish it at higher temperature so that we do not get edge crack. So, what I am telling you or giving you an example is, through metallurgical investigation we know what is the cause of edge crack in austenitic stainless steel, and also we know by looking at this figure, this is a figure based on maybe 100 such coils of AISI 304. So, ferrite content has been shown against finishing rolling temperature. It indicates that if the ferrite content is more, we have to be very careful about finishing temperature, we have to go to higher finishing temperature, but that may not be always desirable, because higher finishing temperature means the property, the final property of the steel may not is again influenced by finishing temperature. So, it is always better that your ferrite content should be low, so that this special care you need not take during finish rolling temperature. So, you can finish roll at any desirable temperature if your ferrite content is less than 7%. There will be no edge crack at all in AISI 304. Let us go to another example. Here what I am showing is, on the left is an etched sample, on the right is the same sample before etching under polished condition. I had mentioned that while you are doing metallurgical investigation, sometimes you have to do both polishing and etching. Under polished condition, certain features are preferably better understood, like inclusions. Normally you look at inclusions under polished condition, because they are better delineated, inclusions are better delineated, and it is not getting confused with other micro constituents or microstructure which get revealed under etched condition. So, on the right here, this is the polished condition. So, under polished condition, how the transverse crack, it is a section, is a crack, we have taken a transverse section and we looked at how the crack is, how does it appear. So, under polished condition we see what is the exact shape of the crack, we can see it in quite better way. Now, when we etch it, then the crack, this is the left one, this is the etched condition. Here the crack, actual morphology of the shape of the crack is not properly revealed, but because of etching, what you can see, the microstructure just adjacent to the crack and away from the crack is properly delineated. So, we find that the microstructure just adjacent to the crack, it is decarburized, there is some scale, there is some internal oxidation. So, these you can see, or you can also see part of it in polished condition, and also the decarburization you cannot see under polished condition. You can see internal oxidation, you can see scale in polished condition just adjacent to the crack, but in etched condition you can see, very easily see, the decarburization gets properly revealed, because you can see that it is relatively wide, that means the amount of perlite is relatively less adjacent to the crack, which indicates that there has been extensive decarburization, which also indicates, because of internal oxidation has been there and scale has been there, that means this crack has got open, that means open to the environment, open to the air. So, the crack has been generated at certain depth, but the crack has come to the surface, and because of that there has been internal oxidation, there has been scale formation, and there has been decarbonization formation. All these have finally given the defect, but we should know how the defect had got generated. So, it is basically crack, while it had come to the surface it has got oxidized. So, the culprit is the crack which has come to the surface during processing or rolling. There is no entrapment here, in no presence of entrapment, we have not detected any entrapment or NMI, non-metallic inclusion adjacent to the defect. The defect is essentially crack which was inside the maybe internal or subsurface crack in the cast product, but during rolling it has come to the surface and has got revealed. Not only got revealed, it has scale with it because it is getting oxidized, it is internal oxidation symptoms, and there is decarbonization. So, these symptoms, decarbonization, internal oxidation, presence of scale, they tell you these symptoms why you are finding through optical microscopy, that is through metallurgical investigation. These symptoms will tell you that this has been caused, this defect has been caused in presence of crack coming to the surface. So, metallurgical investigation helps you in identifying the cause of the problem. So, I am just giving you the same location in polished condition and also after etching. So, polished condition indicated proper shape of the crack, it indicated symptom of scale as well as internal oxidation, but etching along with these two symptoms also indicated there has been decarbonization, which also reinforces the theory of oxidation, theory of the crack coming to the surface and getting oxidized. So, this is another example how metallurgical investigation can throw light on the genesis of the defect, on at what stage the defect has been created. So, this defect has been created during the early stage of hot rolling, when the defect has come to the surface. So, crack was present in subsurface region, that is the defect, origin of the defect, and during hot rolling initial stage it has come to the surface, got oxidized at high temperature. This is a SEM image, scanning electron microscope image. Look at the oxide particles, how these oxide particles have been formed. They have formed at defect location. There was a defect, normally we see the defect, but we wanted to know where from the defect was generated. So, we took the sample, cut a small piece carefully without destroying the defect area, and wanted to see it on the scanning electron microscope. When I put it on the scanning electron microscope at a magnification of 1000, this you cannot see well under optical microscope. The magnification 1000 you can get, but you see the how the different constituents have been revealed. What is the depth of the resolution? You get much better resolution because it is a scanning electron microscope. So, how oxide particles which are very fine, which are maybe 5 micron or 2 micron, maximum 10 micron in size, less than 10 micron. So, how these oxide particles have got generated due to internal oxidation at crack interface. So, this crack was there in the cast slab, either surface or subsurface. Then during the first stage of the initial stage of hot rolling itself, they got severely oxidized, or maybe they got oxidized in the reheating stage itself, and there is enormous amount of oxide formation. These small particles, round particles, these are all oxide particles. So, scanning electron image can reveal these oxide particles, which indicate that internal oxidation has taken place at crack interface, which has been inherited from the cast slab. So, the cast present Thus, the crack present in the cast slab has surfaced at the initial stage, either during your reheating of the slab itself or during initial stage of hot rolling, and severe internal oxidation has taken place at that high temperature. So, the culprit is crack at the surface or subsurface of cast slab, which has generated this defect. So, metallurgical investigation using SEM has been useful in identifying this problem. Now, look at another defect, and this also has been seen under SEM, scanning electron microscope image. So, we find that how the defect looks like. It looks like it is typical. I was telling you earlier, the surface lamination defect is a typical surface lamination problem, as if the surface has got torn, the defect area, it is a jagged sort of surface, and on that you find lot of inclusions. You find here some inclusion, you find here some inclusion, you find here some inclusion, find here some inclusion on the defect area. Defect is a surface laminate. This is a normal surface, this is the surface lamination defect area, and within the defect area you are finding, at defect location we are finding exogenous inclusions. These exogenous inclusions we can know using WDX or EDX what are those inclusions, where from they have come. But in this picture I am just showing you the defect area, how these inclusions are sitting on the defect areas. These inclusions have created the exogenous inclusions have created the defect. So, this defect is generated because of entrapment of these exogenous inclusions, and the inclusion, each inclusion as such is not very large, maybe 30 micron, maybe 20 micron, but since many of them are present, that is why I had mentioned you earlier that in evaluating or in investigating the defect, we must understand what are the inclusions, how many inclusions are present. Too many small inclusions present in a cluster is also a problem. One minor inclusion, small inclusion of 10 micron, 20 micron may not create problem, may not create defect. But if 20 micron, 30 micron inclusions present in large numbers in a particular area, they might create a defect. So, cluster of inclusions might generate this defect. I had shown you earlier this picture, I think this surface lamination along rolling direction. The surface is as if coming out from the another generation of another surface, sort of internal surface. So, this is due to what? Metallurgical investigation has revealed there is large exogenous entrapment in liquid steel or longitudinal crack or depression present in cast slab. So, it can be either large exogenous entrapment in liquid steel or longitudinal crack or depression present in cast slab, which has created this problem. So, again metallurgical investigation has revealed how surface lamination type of defect can be generated either from large exogenous entrapment in liquid steel. As I mentioned, exogenous entrapment can come from many sources, can come from refractory erosion, can come from reoxidation, can come from slag entrainment or entrapment. Whatever is the source, if the size is large, it is a source of problem, it can create problem. Also I have mentioned that longitudinal crack or depression, if they are present in cast slab, then also it might create surface lamination. Yeah. Now look at how a defect gets revealed under SEM under different mode of imaging. On the left I have shown it is secondary electron image. This is what normally scanning images look like. It has got some 3D effect, that means there are many inclusions, small inclusions, they are present in a band, inclusion band. It is an inclusion band having many number of small inclusions. So, in secondary electron image it will look like this, as if inclusions are embedded on the surface. But look at the other mode of image, this one on the right. It is the backscattered compositional contrast. That means, it is giving compositional contrast and the electron is coming by getting backscattered from the surface, steel surface. So, this mode of contrast gives compositional contrast based on atomic element. If atomic elements are less, those areas will appear to be dark, because the less signal will come out, and those areas which are appearing as bright, they are having relatively higher atomic number. So, the steel which is having iron and manganese, say mainly, so they are having relatively high atomic number compared to inclusions which are basically oxides. So, oxides, because of oxygen, presence of oxygen, the relative atomic number is less in oxides. So, inclusions, their atomic number, relative atomic number is less compared to steel matrix. So, steel matrix is appearing as bright, but the inclusions are appearing as dark. So, you know that those are inclusions, those are oxides. If they are real oxides or carbides or nitrides, that you can know using WDX, because you can know from the wavelength or energy of the X-rays what is present there, which element is present there. But in backscattered mode, you can know that these are inclusions which are delineated by the dark image, which is in contrast to the bright image of the steel matrix. So, this indicates that surface inclusion band is revealed differently in different modes of SEM. So, this is just an example showing how scanning electron microscope can, under different modes, can generate lot of information, can generate useful information for identifying the source of the problems, source of the inclusions, the source of the cracks which are creating the defects. Yeah, I have been talking about, that suppose there is an exogenous entrapment in a defect area and you want to know what is the constituent, what are the elements present. First you have to know what are the elements present, then only know what are the constituents present. So, this is a typical example of energy dispersive analysis of an exogenous entrapment. What do you see? How different element, the energy, as I have told you, energy dispersive analysis of X-ray EDX will give you the energy levels of different elements which are generating X-rays. As I have told you, in scanning electron microscope, electron is falling on the sample, it is generating lot of signals. One important signal is X-ray, and depending on whatever elements are present in the steel, different energy of X-rays will be generated, different wavelength of X-ray will be generated. If you can measure the energy, if you can measure the wavelength, then we know what are the elements present. So, energy dispersive analysis of X-ray, the whole idea is to discriminate the energy level of X-rays which is getting generated from the steel sample and from the defect area, from the entrapment, to know what are the elements present in that constituent, in that entrapment, in that non-metallic inclusion. In steel we know what are the elements present, but in non-metallic inclusion what are the present, let us see. So, we see that you see the silicon and magnesium, the left two peaks, these two peaks, this is silicon, this is magnesium. The position of these elements are fixed from the energy level. You see the X-ray is getting generated and the horizontal axis has a different energy levels. So, all elements will be identified or shown at a particular location depending on their X-ray energy level. The silicon, you see the silicon peak is quite high, that means lot of silicon is getting generated, lot of magnesium is getting generated. Where from this is coming? It cannot come from steel, because steel is basically, this is stainless steel. So, it has chromium, it has iron, it has some manganese. So, those are the elements which are present in steel, but overall on top of that we have two peaks, very prominent peaks of silicon and magnesium. So, basically it indicates that this exogenous entrapment is magnesium silicate. So, how EDX analysis first identifies, or WDX analysis can, WDX analysis will discriminate through wavelength, and this one has discriminated from the energy value. This is the difference between the two. So, this has indicated what are the elements present in the entrapments. It has indicated that silicon and magnesium are quite high, and oxygen of course is there. So, it is basically magnesium silicate MgO-SiO2 combination. So, where from it has come, that now if you know steel making, we can identify, we can tell. So, the whole idea of this metallurgical investigation showing this figure is to tell you that how different aspects of metallurgical investigation reveal additional information which will give you, finally will come to a conclusion as to the source of the defect. Though this entrapment is caused by magnesium silicate. So, it is normally expected that it has come from some refractory erosion. Magnesium silicate is a very common refractory used in steel making vessels. So, it has come from there. So, refractory erosion has been a problem, either the refractory quality was not okay, or there was too much of turbulence during steel making which caused erosion of refractory. Now, this is a defect area. There was a crack formation in the cold rolled product. We have taken the transverse section and we have found, on the left side you will find that deformed grains, the grains on the right hand you find normal grains, but on the left, which is a transverse section, you will find grains are deformed. That means adjacent to the defect, grains got, on the right hand side you find normal grains, normal structure, where there is no defect. On the left hand side in the defect area you find deformed grains. So, you know that the genesis of the problem is due to cold deformation, excessive cold deformation, lack of lubrication. That is why grains have got deformed, which is unusual microstructure. So, here normal optical microstructure has revealed that in the defect area grains had got deformed, in the, which is different from the normal grains which is present in the defect free area. So, which indicates that too much of deformation in the cold deformation stage, cold rolling stage has created this defect, either due to lack of lubrication, or maybe lubrication was not proper, or the deformation level was quite high. So, this is the cause. So, again this is another indication, another metallurgical indications which has shown certain symptoms. From there rather you can know what was the source of the defect generation, what was the genesis of the defect. Now, let us see, I have talked about tears on cold roll surface. When I had mentioned the common defects, I had talked about that sometimes there is a tear formation or hole formation on cold roll surface. So, at the top you see at SEM we have seen, just to get a 3-dimensional contour, even at 15 magnification we have seen how the tears look like on cold roll surface, as if something has got torn on the steel surface. So, how the tears look like at SEM at a magnification of 15 only, at a very low magnification, because these tears were seen under normal with normal eye. So, even at 15 magnification you can very clearly see how they look like. Now, why they have formed, why they have got generated? To reveal the information you have to go to higher magnification under SEM, because as I have told you, SEM the depth of focus is more, you can get, even if there are crack formation, it will reveal many things which optical microscope cannot reveal, because optical microscope uses normal light, but the depth of focus is not more. Depth of focus is inversely related to the wavelength of the medium. In optical microscope the medium is normal light, and electron microscope the medium is electrons. The wavelength of electrons is much lower compared to normal light. That is why the depth of focus, which is inversely related to the wavelength, which is much better for optical rather or for SEM, electron microscope. So, when we are using electrons to see the microstructure in scanning electron microscope, we see a much better depth of focus, much is a 3-dimensional effect we can see. Now, look at what at 150 how does the tear look like, and a portion of the tear at 1000, you see how this SEM observation reveals excessive stress generation during deformation. Why excessive? Because you find some crack formation just ahead of the tear. You can see the tear at low magnification, but at high magnification, say at 150 or 1000, it is very clear. You see how there has been a crack formation, there is fine tears ahead of the main tears. Main tears you are seeing even in normal eye, that is the defect, but just ahead of it you see fine cracks. Now, why these fine cracks are formed? There is no entrapment or nothing. These have formed because of too much of excessive deformation, excessive stress generation. These cracks have formed, these fine cracks have formed ahead of the tears. So, again scanning electron microscope 3-dimensional effect has revealed a generation of many cracks, fine cracks or tears ahead of the actual defect. Actual defect was the tear, but if you look at the adjacent area you will find lot of symptoms which will indicate how the cracks have formed. So, here we find lot of fine cracks which indicate or reveals that excessive stress got generated, then only there will be crack formation. Crack on its own crack will not form. So, that means under normal plastic deformation you will not find crack unless you have very excessive, which is beyond the limit of the steel, particular steel which you are using. So, excessive stress generation has created defect. So, we know from here from metallurgical investigation how defect has got formed, where from it has got generated. So, this is the source of defect. Here the cause is not a entrapment, not a pre-existing crack in the cast product, but this is formation of tear on cold roll surface because of excessive stress generation, maybe lack of lubrication, maybe bad lubrication, maybe excessive cold deformation, cold amount of deformation. So, here the culprit is the cold processing, not steel as such, okay. Because earlier I had mentioned the reasons or the generation of defects which are traced back to the quality of steel, either entrapment or crack existing in cast product. But here is a situation which are tears formed in cold deformation. These are nothing to do with no entrapment and no deoxidation, nothing is there. So, these cracks have formed during cold deformation, they are not existing in steel. So, it is not a material defect, it is a process defect. So, I have talked about different types of defects which has got revealed during metallurgical investigation, and the whole idea to show these defects is to reinforce that how metallurgical investigation, these are some examples, very common examples of quality problems, just to show you how metallurgical investigation has revealed or has been useful in identifying what are the quality problems, at what stage they got generated, and if you know these, then only we can identify how we will take care of these problems. Thank you very much for your kind attention.